Hey you guys, this is Mr. Sal. Thanks for watching. We're going to be looking at the homework from 9.3 in this probability unit. So it's just a few select problems that we had and we're able to go through because of time. So thanks for watching again. Please subscribe and comment below, and we'll catch you guys later. M&M probability. The color mix in a large bag of M&Ms is shown in the table. What is the total number of M&Ms in the bag? So to find the total number of M&Ms, we just need to add all these numbers together. And when we do that, we should get 220 M&Ms. Alright, 220 M&Ms right here. So as a fraction of the reds, there's 60 reds out of the 220. There's 40 greens out of 220. There are 45 browns out of 220. And the rest of these, same idea. Next up, to find the percentages. For example, red, we do 60 divided by 220, but then we multiply that result by 100 for the percent. So I'm going to round this to the 10th. It didn't really say where to round, so I got the 10th right here. We'll do the same thing for the rest of these as well. Alright, so these are all the percentages after we divide and multiply by 100 for the M&Ms of each color. Number 4, suppose you went to the store and bought a large bag of M&Ms. From that bag, you took a sample of exactly 50 M&Ms and calculated the percent of each color in your sample. Do you think the percents would be the same as in the first table? Why or why not? Well, we need to expand on some of those, okay? So first of all, if we expect each bag to have about the same number or the same percentage of colors, then we would expect it to be the same. But since it is experimental probability radicale, we may expect some differences in the percentages as well. So it all depends on how you look at it, whether there is or is not. The bag game is pretty nice because we've got 3 bags right here.
Really? Oh.
We've got this bag with 25 reds and 5 of the other. We got this bag with 20 reds and 10 of the other. And then we got 10 reds and 20 of the other. So this one has to do on preference. For example, you're given, to make your guess, you're given 3 options. Looks like it's 5 options actually. A, you can either draw 5 chips out of the bag, and if you guess correctly, you get a win $100.
Wow.
If you get it wrong, you get $0.
Oh.
If you want to draw 10 chips, you get 75, 15 for 50, 20 for 25, and 25 for 10. So this all depends on if you feel like you're understanding this probability stuff, really. So what they do is they give you a bag, either the black, purple, or the green one, and then you can draw those number of chips, and if you can guess correctly which bag you have, then you get that amount of money. So if you're drawing 5 chips, it's not a lot right there. It's about 1/6 of the chips. You'd have to be pretty confident that you got it, but experimentally it's possible that you could draw all of one color. So it just depends on what you feel comfortable with here. So maybe I would go with something like B, because that's 1/3 of the chips for a lot of the money. And with 10 chips, I feel pretty confident that I could guess which bag I have right there. For example, if I had pulled out of the 10 chips, maybe 7 reds and 3 of the other color, then I would be looking at either the black or purple bag right there. But it just depends. It just depends. But I would feel pretty confident with 10. Not as confident with 5. I know for sure if I draw 25 chips, I can tell you which bag I have, okay? Or which bag you've given me. I guess we should know this. To play the game, when you take a color out, you record the color, but then you put it back. That's still pretty good. I mean, you should theoretically be able to tell which bag you have based on that experimental probability that you have. So You want to win as much money as possible. Which option do you choose for guessing which bag? Again, it depends. There's no real right or wrong answer for this, though. It just depends on what your explanation is. Alright, number 6. If you roll 2 dice 36 times, how many doubles would you expect to see? Well, we know there's only 36 theoretical outcomes for rolling 2 dice. And doubles would be something like getting a 1 and a 1, a 2 and a 2, a 3 and a 3, and so forth. So we see right here that there's only 6 ways to get doubles out of 36 possible outcomes. So how many doubles would we expect to see? 6. So what is the probability of rolling doubles for 2 fair die? We already got that one right here. Suppose you roll the dice and toss the coin at the same time. Create a probability model. Both a tree model and table, which is fine. For rolling a die, then tossing a coin once. Alright, so we got 2 things that were going to happen. We're going to roll the die, and then we're going to toss the coin, and then that should produce our outcome. Alright, so for the dice, we know you can roll either a 1, 2, 3, 4, 5, or 6. Now from there, let's say if you tossed a 1, then you could either toss heads or tails from there. Same with 2, you could either get heads or tails. 3 would give us heads or tails, and this continues. So let's go ahead and look at the outcomes then. For each one, for example, this one would be a 1H. Alright, so there is our tree model, just to start out with. And the area model may make even more sense. It's up to you, really. So for the table, right, we got first, I'll put the dice right here. And then the coin will be on the top. Okay, so for the coin and the dice, we got different outcomes. The coin, it is possible to toss either heads or tails. And for the dice, you're looking at either 1, 2, 3, 4, 5, or 6. And then this creates our table like this right here. So the outcomes, again, this is a 1H, 2H, 3H, and so forth. Same outcome, same number of outcomes even. And as it turns out, that is a sample space.